In this exercise, we will demonstrate the cable sizing tool. The cable sizing tool can be used to verify existing cable types in the network and to suggest recommendations to improve cable types, in order to meet voltage, thermal loading and short-circuit constraints. Activate the cable reinforcement study case in the project overview window. Here you can see the 400-volt network. Color the network to show any feeders that are present in the network. Here you can see one feeder is present. We're going to carry out a cable sizing analysis on this particular feeder. Zoom in on the feeder and double-click on the substation at the center of the feeder. Run a load flow. You can see with the existing cable types, that the feeder has a minimum voltage of 0.91 per unit, a maximum voltage of 1.0 per unit and a maximum voltage drop of 9.32%. You can see that this voltage drop is quite high, and could be improved. Ensure the cable analysis toolbox is selected, and choose the cable sizing icon. We will use the cable reinforcement method, where cables are selected from a user-defined selection of cables and against a user-defined selection of constraints. Ensure that the feeder we wish to carry out the calculation on, is selected, and to start with, we will carry out the verification only. We will use a balanced network representation. Execute the calculation. Results are shown in the output window. In the first section, any cables which are exceeding their thermal loading limits are identified. You can see here that 3 cables are exceeding their thermal loading limits. Cable LN1216 consists of a number of subsections. It can be seen that subsection 2 is overloaded. Cable LN1372 consists of just one section, and this whole cable is overloaded. Cable LN1348 is overloaded as well. These cables are considered overloaded, because they exceed a specified overloading constraint of 100%. In section 2, you can see results for every bus in the feeder, where voltage constraints are exceeded. You can see again, that the maximum voltage deviation along the feeder, is minus 9.32% voltage drop, which corresponds to a bus voltage of 0.908. Terminals are included in this list, if their voltage drop exceeds a specified constraint of 5%. So on the basis of these results, you might want to consider altering the cable sizes in the network, to improve performance against the considered constraints. Run the cable sizing tool again. This time, we will change the mode to recommendation. Look at the cable types contained within the selected cable type folder. This is the library of cable types, from which the cable sizing tool will determine the best types of cable to use. Notice that on the Cable Analysis tab, costs have been attributed to each of the cable types. Costing will therefore be factored in, when optimizing the selection of the cable types. On the Constraints page, select the option Thermal Loading Limits, and ensure that no line is overloaded by more than 100%. We will also select the option Voltage Constraints along feeder. So we will allow for a voltage drop of no more than 5%. On the output page, check the Modify Cable Types box, and choose the option Create a new variation with recommended cables. Select Execute. You can see that a new variation has been created and activated, containing the new cable recommendations. In the results summary you can see that load flow results have now improved. The minimum voltage is now 0.95 per unit and the maximum voltage is 1 per unit, and the maximum voltage drop is 4.97%. This is within the voltage constraints that we specified. Looking at the output window, you can see that the verification is taking place again. And on the third box, you can see the recommended cable exchanges. The existing cables are shown, and the recommended cables are shown. In the final section you can see the costs of the reinforcement.